Welcome to A Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about photoelectric effect from Cambridge A2 Physics. In this lesson, I will explain you what is threshold frequency, how threshold frequency and work function are linked with each other, and what is the relationship between intensity and frequency of light with the help of past paper questions. Part A1 is simply asking us what is meant by the threshold frequency. Threshold frequency is a very basic concept in this chapter and we need to be very clear about this. Let me explain to you what is threshold frequency. Threshold frequency we can simply understand. Let's say we have a piece of metal and this is the electron located at the surface of the metal, and a photon of light is coming, and when this photon of light reach the surface and absorbed by this surface electron, the surface electron is emitted from the surface with zero kinetic energy. So threshold frequency simply means that the lowest frequency of electromagnetic radiations we need for the emission of photoelectrons from the surface with zero kinetic energy. So often we use F0 for threshold frequency. Let's try to state what is threshold frequency. This is how we can state what is meant by the threshold frequency. So simply the lowest frequency of electromagnetic radiation we need for the emission of photoelectrons from the surface of a metal, and threshold frequency is different for different metals. The next part is simply asking us we need to calculate threshold frequency for platinum, means is for this metal. Its work function is given to us, so how we can calculate threshold frequency. The first thing what we need to understand is that the work function of a metal is equal to the product of Planck's constant times threshold frequency. If we need to calculate threshold frequency and work function is given to us, we can simply divide that by Planck's constant. As in this case, work function is given to us, so we simply need to divide this work function by Planck's constant. And this is how we can answer this. As you can see here, I have already calculated. Very straightforward one if simply you understand work function is equal to product of Planck's constant and threshold frequency. For part B, a continuous spectrum of wavelengths between 300 and 600 nanometers is incident on each of the metals listed in figure 7.1. These are the metals we have here. This is first metal is sodium. Its work function is given and threshold frequency is also given. Next one is zinc. Its work function is given and its threshold frequency is also given. The third one is platinum. Its work function is given and we have already calculated its threshold frequency, that was equal to 1.4 times 10 to 15 Hertz. For this question, we simply need to determine which metals, if any, will give rise to the emission of electrons. First thing what we need to understand is the basic condition for the emission of electron from the surface of any metal. So that basic condition is simply if the frequency of photon, means the frequency of incident photon, is greater than the threshold frequency of any metal, then photoelectrons may be emitted. So this is the basic condition. We simply need to calculate the frequency of photons and then we need to compare with threshold frequency of metals. If the frequency of photon is greater than threshold frequency, photoelectrons will be emitted. If it is lower than threshold frequency, photoelectrons will not be emitted. First of all, let's try to calculate frequency of each photon. So here we have calculated frequency of each photon. For this photon, its frequency we have also calculated. If we look at this frequency 1.0 times 10 to 15, this frequency is lower than frequency of platinum, because frequency of platinum we have calculated that was equal to 1.4 times 10 to 15. But this frequency is greater than frequency of sodium and also greater than frequency of zinc. So it simply means that photoelectrons will be emitted from sodium and zinc. So this is how we can answer this question. For part C, when light of a certain intensity and frequency is incident on a metal surface, electrons are emitted. Question is simply asking us, we need to state and explain the effect on the rate of emission of electrons if we keep the intensity of the light same and we increase its frequency. It simply means that we need to understand the relationship between intensity and frequency. So let's try to understand how frequency and intensity, they are linked together. First thing we understand, intensity is equal to P over A, or we can say this is equal to energy over time times area, and E is the total energy of all the photons. We can replace this E with energy of single photon. So we can rewrite this formula. We can say this is N times E naught over T times A. So here this is the intensity, and E naught, this one, is energy of single photon. So this is energy of single photon. So we can write down here. Now the next thing we need to understand is that the energy of photon is linked with its frequency. We can say E naught is equal to HF naught. HF naught. Now if we increase the frequency of the light, mean frequency of the photon, its energy will increase. We can also say that if we increase this energy but we are not changing the intensity, what is the effect on number of photons? So it simply means that number of photons will go down. So this is the main idea what we need to understand. If we understand this one, so we can simply answer this question. So this is how we can answer this question, and then I will explain you again why I wrote like this. So the first thing you can see here, each photon has larger energy. As you can see here, if we increase the frequency of the photon, its energy will increase. Second, fewer photons per unit time means the number of photons will decrease. And if the number of photons are less, it means less number of electrons will be emitted. So we can say fewer electrons will be emitted. Each photon will give rise to the emission of one electron. If we decrease the number of photons, number of photoelectrons will also go down.